Flow matching is the newest paradigm for image and video generation. It was adopted by most open source models, including CDANs, Flux, and Stable Diffusion 3, and probably proprietary ones as well, though we don't know for sure. Compared to traditional diffusion models, flow matching refines a noisy frame into a well-formed image in fewer steps, maybe 2 or 3 instead of 10 to 20. The two methods have been proven to be mathematically equivalent, but in this video we'll cover the flow matching perspective. The algorithm itself looks deceptively simple, almost naive, and makes you wonder, why does it work at all? And also, if it's so simple, why didn't we start from here? Why did we go through diffusion? So we'll make sure to dig deeper and uncover its foundations, both in mathematics and in physics. Along with this video, I made a companion tutorial that you can find at diffusion.fyi. You can follow at your own pace and play around with the interactive animations. It's completely free and doesn't even require sign-in. If you're interested in diffusion, you can find more tutorials there, or I have an entire YouTube series on it. But for now, back to flow matching. Captain Obvious says that images are made of pixels, and each pixel can be seen as a separate dimension in a multidimensional space. But as human mortals, we'll have to settle for a 2D visualization where the two axes represent pixel intensities. This blue cloud represents a probability density. Bright regions are more likely to contain meaningful images, and dark regions are full of noise. We'll call this density P data because it reflects the true but unknown density of the data. The ultimate goal of generative modeling is to learn P data from a set of training images. That way, at inference time, we can generate new ones unseen during training. Older models, like generative adversarial networks or GANs, attempted to learn P data directly, but their output quality suffered. The issue is, this density is extremely complex to learn in one go. It literally makes a judgment about every possible combination of pixels. So to make this problem more tractable, modern methods like flow matching and diffusion discover P data progressively. They start with a much simpler density P0, chosen programmatically, and gradually evolve it over time. Generative modeling happens in a fictitious time interval from t equals 0 to t equals 1. It's like a progress bar that moves a density pt between the source p0 and the destination p data. In reality, since we don't know the real p data, we'll guide a model towards an approximation of it that concentrates probability mass around the training points. This is the target density p1. This gradual construction mimics how humans create art. A sculpture doesn't just spontaneously appear. It's carved stroke by stroke in small refinements and may take years to complete. We aim to model the individual strokes, namely how our intermediate sculpture, p index t, changes with every small time interval. Formally, that's the partial derivative with respect to time. But what does it even mean to take the derivative of a probability density? That's a hard thing to wrap your head around. Fortunately, physics has been dealing with this problem for centuries. It's the fundamental phenomenon of transport. This involves the movement of a conserved quantity, such as electric charge flowing through a wire or water flowing through a pipe. Probability mass behaves similarly. It is also a conserved quantity, as it always integrates to 1. It doesn't spontaneously appear or disappear. Instead, it simply moves through time and space. This type of transport is described by a classical result from the 19th century, the continuity equation. The continuity equation gives us an expression for the partial derivative that we didn't know how to tackle earlier. It involves a time-variant velocity field vt that transports the density over time. But what exactly is a time-variant velocity field? First of all, a field is something that's defined at every position at every point in time. A vector field in particular defines a vector or an arrow at each such position. But instead of arrows, it's common to draw vector fields using these streamlines. Vector directions are indicated by arrowheads and vector magnitudes by color. We'll use a standard color scale where purple means low magnitude and yellow means high. Most of the time, my vector field plots will ignore their magnitude because it's a bit distracting, but occasionally I'll turn it on when relevant. When we drop a particle in this field, it follows the velocity streamlines, slowing down in the purple regions and speeding up in the yellow ones. This motion is described by a simple ordinary differential equation, or ODE for short. It simply says that distance traveled equals velocity multiplied by time passed, but applies the statement to infinitesimally small intervals. This vector field in particular is constant, but vectors can change both direction and magnitude over time. This is a time-variant velocity field. Now, imagine that we drop an entire cloud of particles onto this field. In fact, infinitely many. That's our blue shape over there. The continuity equation tells us that the evolution of its density in time is determined by how individual particles are transported by the velocity field according to this ODE. It implies a deep connection between global evolution and local movement. So if we train a model to predict this velocity field, then at inference time, we could push particles through it. Start from a point x0 sampled from p0, follow the field over time, and eventually reach a destination that is likely to be a well-formed image. Learning a velocity field is the idea behind flow-based methods. Flow matching is the poster child today, but its lineage goes back more than a decade. Normalizing flow was published in 2015, continuous normalizing flow, or CNF, in 2018, and flow matching in 2023. We won't cover the older methods here, but it's worth asking why they were never state-of-the-art, even back in their eras. Before 2022, the dominant paradigm for image generation were GANs, which were then outranked by diffusion models like Stable Diffusion. The issue was flow-based methods used to be very difficult to train because there's no explicit ground truth velocity field to learn from. The static images in the training set are the final transport destinations and tell us nothing about the journey itself. CNF models used an indirect learning objective that was very expensive to compute. During a single training step, they simulated an entire backwards journey. Start from a training sample x1 and trace the velocity field in reverse all the way to a noisy point x0. From this vantage point, evaluate the likelihood that the model assigns to x1. The training objective pushes the model to maximize this likelihood, since we know it's a real data point. This is known as maximum likelihood estimation, or MLE. Each small segment in this trip is a separate model invocation to get a point estimate for the velocity field. This is what made training so expensive that CNF models simply could not scale enough compared to GANs or diffusion models. Flow matching drastically simplifies training. It removes the need for this round trip by coming up with a way to produce supervised velocity labels. We'll call them V-star. In their presence, the model can be trained with a simpler objective that minimizes the squared distance between the model predictions V theta and the labels V star. This is called the mean squared error, or MSE. Compared to CNFs, this training iteration requires a single model invocation. It's therefore much faster and, under the same computational budget, enables training bigger models on more data. But the million-dollar question is, where do the supervised labels come from? I'll start by presenting the flow matching algorithm end to end. But if you're like me, you might find yourself thinking, this just seems like a random thing to do. Why does it work at all? So if that's your reaction, to bear with me, because we'll take every single step that looks simple and naive and we'll dissect it to understand the reasoning behind it. So here's what a single training iteration in the flow matching algorithm looks like. Pick an image x1 from the training set. Pick a noise sample x0 from the source density. Consider a particle moving in a straight line between these two endpoints. Now pick an arbitrary point in time. calculate the particle velocity here. Assuming it moves at a constant speed, the label v star conveniently simplifies to x1 minus x0. Now, invoke the model at this fixed point xt to get a prediction v theta. Compute the mean squared error between the model prediction and the supervised label, and update the model parameters accordingly. Now, rinse and repeat in a training loop to train a model that learns a time-variant velocity field. There are so many things that, at first glance, look arbitrary in this algorithm. To begin with, x1 and x0 are chosen independently from each other. Compare this to CNF, where x0 was derived from x1 by following velocity predictions in reverse. Then, why draw a straight line between them? Clearly, the true velocity field has some curvature in it. Where will the model learn curvatures from? And don't get me started on the constant velocity label. The true velocity field clearly changes in time, so where will the model learn the time dependency from? Maybe you're smarter than me and the answers to these questions are obvious to you, in which case I'll see you in the next video. But for the rest of us, let's see where these arbitrarily looking decisions come from. At a high level, flow matching proposes a divide and conquer approach to training. The big problem to be conquered is transporting P0 into a single monolithic P1. Flow matching breaks it down into multiple simpler tasks. Each training step selects a real image x1, then it transports P0 into a Gaussian centered around it. So a single training iteration teaches the model how to transport P0 into a density P1 conditioned on x1. To simulate these simpler transports, we need the corresponding conditional velocity fields. Instead of Vt, we'll simulate Vt conditioned on x1, and we'll discuss soon how to do that. Now, a model that only learns how to perform simple P0 to Gaussian transports is not very useful. It needs to know the destination x1 in order to produce the velocity field that leads to it. And of course, at inference time, we don't have access to x1. The whole point is to generate it. However, here's the magic behind flow matching. When a model is trained on these basic tasks, the skill to perform the challenging P0 to P1 transport can emerge automatically. In other words, a model that observes conditional velocity fields can implicitly learn an unconditional velocity field, also called marginal. The flow matching algorithm verifiably has this property. It was really not obvious that such a free lunch existed, and that's probably why flow-based methods took a while to arrive at this formulation. While this realization is incredible, the math behind it is actually quite straightforward. So instead of going through boring calculus, we're going to try to reverse engineer what went through somebody's mind when they realized that training on a conditional velocity field induces a marginal velocity field. To understand the relationship between conditional and marginal fields, we first need to figure out how to produce the conditional field that transports P0 into Gaussian and that acts as a training signal. The first thing to notice is that this field is not unique. The paths could go straight, bend downwards, or even go through a loop. So we need a principled way to choose one of these. There's a branch of mathematical optimization called optimal transport that seeks to answer the following question. Out of all the ways to move a density to another, which one minimizes the squared distance traveled? This is an appealing way of framing the problem because it formalizes a notion of efficiency, and an efficient velocity field will lead to shorter paths and faster inference. That's why we'll choose the conditional field using optimal transport theory. Now, answering this question is generally very hard. If it were easier, optimal transport could give us a recipe for transporting P0 directly into P1. But for Gaussians in particular, there's a straightforward answer. The optimal transport is an affine map. That just means a scaling operation plus a translation. So every point x0 sampled from our density P0 is scaled by sigma and translated by x1. But this map only tells us about the endpoints. in order to gradually morph one density into another, we can use a result that dates back to 1997. It tells us that the optimal way to deform one Gaussian into another is to linearly interpolate between x0 and its image t of x0. This gives us an expression for all the intermediate points xt on the conditional path. This is actually the expression that I used to draw these shaded cones. And it's actually the linear interpolation in the flow matching algorithm, just with standard deviation sigma set to 0. Setting it to 0 is very common practice in real-world models. A non-zero sigma helps avoid all sorts of edge cases in theoretical math, but doesn't make a difference in reality. Once we understand optimal transport between two Gaussians, the first three steps of the training algorithm should now make sense. x1 is the mean of the target conditional distribution. Sampling a single x0 and drawing a straight line to x1 is a way of taking a transport sample from this shaded cone. Drawing a straight line is not an arbitrary decision anymore. It's a way of implementing optimal transport, not between two arbitrary points, but between two Gaussian densities. The next uncomfortable part of the training algorithm is this constant velocity label. It's derived from the optimal transport paths. Since velocity is distance over time, or dx over dt, the math simplifies to x1 minus x0. But to me, this is still unsatisfactory. Even if the math works out, the constant velocity label still seems to be at odds with our ultimate goal of learning a time-dependent velocity field, vt. So where does the disconnect come from? Well, v star is not representative of the entire conditional field. We evaluate it at a very restrictive region of spacetime along the optimal transport paths, and at times when particles are plausibly there. But the full conditional velocity field spans over the entire spacetime. It includes this corner that will never be visited by particles, and it includes this position even at time t equals 1 when no particles would be there anymore. This larger velocity field is indeed time-dependent. The vector directions don't change, but their magnitudes do. Remember, purple means low magnitude and yellow means high. As time passes by, increasingly more of the field is covered in yellow. With less time left for a particle to reach its destination, the velocity field needs to push extra hard. In fact, at t equals 1, when time completely runs out, magnitudes explode to infinity. But again, we choose to evaluate this velocity field along the optimal paths. If we track a single particle, we'll see that it moves along this field in a way that catches up with a change in field magnitude. From its perspective, velocity is constant. But rest assured, the full conditional velocity field is still time-dependent. There is one more issue with these velocity labels. Consider two training steps. The first one samples endpoints x0, x1, and time t. The second one samples two different endpoints, but the same time t. Their interpolations intersect at point xt. Now here's the conundrum. For the same input, our model will now see two different velocity labels. They can't both be correct, so are we training the model on garbage labels? The saving grace is the specific choice for the loss function. As we saw before, flow matching uses the mean squared error loss to minimize the distance between a model prediction v theta and the velocity label x1 minus x0. Given conflicting labels for the same input, it can be shown that a model trained with the MSE loss will learn their weighted average. So in this case, the learned model prediction v theta will be somewhere in between the two v stars. Okay, so the model has a well-defined behavior on conflicting labels, but is learning their average useful? Well, it turns out that this weighted average is the marginal velocity field. So the MSE loss drives the model towards the correct marginal because of the conflicting labels, not despite them. To build an intuition, consider many conditional training paths at once. The teal cone is a region swept out by many training paths heading towards X1, while the orange cone is an analogous region for many training paths heading towards X1 prime. The learned model paths are drawn in red. Let's look at their behavior. Outside the cone intersections, each path follows the straight supervised signal toward the original destination. But within the cone intersection, where velocity labels are conflicting, the averaging effect of the MSV loss leads to this curvature. The model ends up pairing the endpoints differently from training. X0 is connected to X1 prime, and X0 prime is connected to X1. There are no more intersections, just curved paths. This is the intuition behind learning a marginal velocity field. If you want a more rigorous proof, you can find it in the original flow matching paper. So once a model V theta is trained, generating new samples is straightforward. Start from noise and follow the learned velocity field forward in time using this ordinary differential equation. Solving the ODE from t equals 0 to t equals 1 yields a generated sample x1. In practice, we can solve the ODE analytically through integrals, so we approximate it numerically. The simplest approach is the Euler method, which chops the time interval from 0 to 1 into smaller discrete intervals. Each step requires one model invocation, one forward pass through the neural network. The exact number of required steps depends on how curved the learned velocity field is. If the field induces nearly straight trajectories, even a single step might suffice. If the trajectories curve significantly, then more steps are needed to stay on track. This is why trajectory curvature, the phenomenon we saw emerge from conflicting velocity labels, directly impacts the inference speed. This brings us to rectified flow, the concurrent work to flow matching that independently discover the same foundational idea. Learn a marginal velocity field from conditional straight-line velocity labels. But on top of that shared foundation, rectified flow proposes one extra step to reduce the curvature of the learned velocity field. So the root cause of curvature are the intersecting training paths, and the root cause of intersections is the independent coupling of the endpoints in the vanilla flow matching algorithm. Remember, I complained about this. So how could we choose X0 and X1 more strategically? Rectified flow proposes a second training procedure. Once a vanilla flow matching model is trained, it acts as an endpoint matchmaker. Start from a random point X0, follow the trained model velocity field, and land on a real image X1. The X0-X1 pair is no longer independent. Producing a fresh training set this way will result in fewer intersections than random coupling. The second training stage is called reflow. With every reflow, the induced model paths are straighter and straighter up to a point where a single Euler step might be enough. This is effectively a one-step generative model, as fast as GAN, but trained with a much more stable flow matching objective. Hopefully, the flow matching training algorithm looks a lot less arbitrary by now. The one big topic I haven't covered is the equivalence between flow matching and diffusion. If you want to see a side-by-side comparison, let me know in the comments, otherwise I'm ready to move on to other topics. Don't forget to check out diffusion.fyi. It's free with no sign-in required, but feedback is much appreciated. Thanks for watching, and I'll see you next time.